Now we'll take up another type of control source, which is a current controlled current source. And just like with the voltage controlled voltage source, we will make the gain of the current controlled current source to be 1. That is, in general, a current controlled current source should have an output current which is some constant K times the input current, and they should be independent of the impedance of the source which is driving the current controlled current source, and also the load resistance. Okay. For that to happen, it should offer a very small input resistance tending to 0 and a very high output resistance. Okay. Now, because of the way the MOS transistor is, which has a common terminal between the controlled and controlling sides, that is, the source terminal is common to the two sides, it turns out that we can only realize K equals 1. Okay. So we will try to realize I naught equals II. Again, as with the case of the voltage controlled voltage source, although there is no gain, this is still useful as a current buffer. Okay, meaning, let's say we had an imperfect current source II in parallel with some source resistance Rs. And if you have a source resistance and if you have a load resistance RL, if you connect it directly, the load current, okay, will be just a fraction of the input current. And how much this fraction is depends on the ratio of Rs to RL. Okay. Now, if you use a current buffer, this is a current buffer, it will have a very low input resistance, meaning all of that current will go into the input and the output current will be exactly equal to the input. Okay. So regardless of the values of Rs and RL, the output current, the current in the load, will be equal to the input current. Okay. So that's the use of it, and we will realize this using a MOS transistor. Okay. So we want I naught equals II. When we say there is an input current, obviously we mean that there is a current source whose value is II, and of course it could be non-ideal. In fact, it's expected to be non-ideal, and it will have a resistance in parallel with it, which is Rs. Okay. Recall that our representation for a voltage input is a voltage source Vi in series with resistance Rs. Equivalently, you can think of it as a current source II in parallel with Rs. Okay. So this is our input. Now, in the initial discussion, just to make the drawings easier, I will omit Rs. Okay. Although later I will put it in and analyze its effect. Now I want I naught equals II. And what is this I naught? We have the MOS transistor with its gate, drain and source terminals. This is VGS and this current is GM VGS. And the incremental drain current flows from drain to source, and that will be the output current I naught. Okay. So that's where a current flows in a MOS transistor, and that has to be the output current of our circuit. Okay. So this current flows from drain to source. Now, what do we do in order to realize a current controlled current source? We have to compare I naught, the output current, to II. And if I naught is greater than II, we have to reduce VGS, and if I0 is less than II, we have to increase VGS. Okay. Now eventually the output current of this block must be connected to a load. So the current flows from drain to source. We could connect the load to one of these terminals and do this comparison at the other terminal. Okay. Now if you have been kind of following closely and you recall what we have done in earlier lectures, you see that we have actually done this already. Okay. What we are saying is that the drain current of the MOS transistor ID, here let me rename this ID, we want to make it equal to ID or I0 equal to a given current II. Okay. Now where have we done this before? We have made the drain bias current of a MOS transistor equal to a given current I0. Okay, that we have already done, right? So we have done it for the sake of biasing. Now we will do it for signals. Okay. Now it turns out that the most convenient way of doing it for signals is to essentially copy the source feedback biasing. Okay. What did we do here? We had a certain drain current ID and we wanted to make it equal to a given current source. Let me call it, just to not confuse with the other I0, let me call this I1. We wanted to make ID equal to I1. We connected these two together so that the difference flows into a parasitic capacitor, and if ID is more than I1, it increases the source voltage, thereby reducing the value of ID. The gate is connected to a fixed voltage, and if ID is less than I1, current will be drawn out of the capacitor, the source voltage will fall down, VGS will increase and the current will increase. Okay. Now this is a convenient way of doing it with signals as well. So what do we have to do? The drain current of the MOS transistor is flowing like that, and we connect our desired current. In this case it's the input current, so we call it II there. Okay. So what happens? We have II over here and ID over there, and the gate is connected to small signal ground. Okay. Here it is connected to some fixed voltage, but in this case we just connect it to ground. Now what happens? You can imagine exactly the same thing happening as earlier. You can imagine a parasitic capacitance here, and this difference ID minus II will flow into that one. And what happens if initially ID was too small, then this current will be negative. So current will be pulled out of CP, the source voltage will fall down, VGS will increase and ID will increase. Okay, and exactly the opposite happens if ID is too large. Now ID is flowing from drain to source, so we can use the part that is flowing out of the drain to connect it to a load. Okay, that's a load, and for illustration you can imagine that it's a resistance. Okay, so that's all that's there to it. In this case I didn't discuss the scheme in too much detail, but making the output current or drain current of a transistor to a given current II, we've already done it before for the sake of biasing. Here we have made this total current ID equal to this given current I1. Now what applies for total current definitely applies for incremental currents, and we used exactly the same scheme. Okay. The negative feedback action must be pretty obvious by looking at how much current flows into the CP, and it depends on the difference ID minus II. Okay. So this is our current buffer or current controlled current source, or at least this is our attempt at getting one such block. Now you can see that in steady state no current flows through the capacitor, and all of this II will flow through here. What it really means is that VGS will adjust itself so that the current flowing here, Gm times VGS equals II. Okay. Now we can analyze it further to see whether it really does that, and also to see what its input and output resistances are. Okay.